right. So we've got, I guess, like 3 lectures left, and we're sort of nearing the end of the thread that I've been weaving through this class. We're gonna start to have some lectures in which I try to just bring in a couple of other topics for fun. This last one, I've still managed to weave it into the story of the class. Next two, maybe less so. But what I want to talk about today a little bit is something called differential privacy, which something that was not developed with game theoretic applications in mind. It was something you might come across in your lives otherwise, that was sort of developed as a way to, it's sort of a solution concept for privacy, a way to do computations on private data with provable guarantees that you don't reveal too much information about the data of the people you're computing on. But like, as it turns out, it also has some rather direct connections to auction theory, which is the avenue through which I'm going to talk about it today. Yes, so the way I'm going to sneak differential privacy into this class is through this vehicle of digital goods auctions that we've been studying for the last few lectures as sort of like a test bed for techniques in which we've, in various settings, tried to maximize revenue in auction design, right? So this was the setting in which we developed like the random sampling auction and these various online auctions derived from learning algorithms like the polynomial weights algorithm and the UCB bandit learning algorithm. And if we just sort of like remember back to maybe state of the art for what we know about revenue maximization in this digital goods auction, well, we know a couple of things. The random sampling auction gave us, in like a static setting, like a factor 4 approximation, if you remember, right? The random sampling auction allowed us to get within a factor of 4 of the revenue of the optimal fixed price in these digital goods auctions. And then we gave, this sort of online auction via the polynomial weights algorithm that had a sort of incomparable guarantee, but that you might view as better than a 4 approximation. It gave sort of this additive loss. It said you could do as well as the best fixed price in hindsight, that was the revenue obtained by opt, minus something that looked like the regret term of the polynomial weights algorithm, which was like, if there's n bidders, like root n. Okay, if 1 bidder arrives over time. And if, we sort of said, okay, well, if opt grows somehow linearly with the number of bidders that arrives, which is the kind of thing you'd expect if you've got unlimited supply, well, this is better than a 4 approximation, because asymptotically, as n grows large, you'll sort of approximate the optimal revenue exactly. But we might still hope to be able to do better than this. Like why root n there? Why not something smaller like log n? And the thing that we're going to try to do in this class is to get a much better guarantee here, to replace this like root n with something like a log n at the cost of something, at the cost of asking for something that is a little bit weaker than what we've been asking for in the class thus far. So far, we've been asking for dominant strategy truthfulness in every auction we design, which means that, no matter what your value is, no matter what everyone else bids, you cannot gain by even a little tiny bit by trying to be strategic and misreporting your bid. Okay, which is pretty good. But we're going to sort of, in this class, sort of ask, okay, well, what if I'm okay with the possibility that you might be able to gain a little tiny amount, like an infinitesimally small amount, by misreporting, and that you do sort of essentially as well as you could possibly do by telling the truth, right? Maybe you could gain a tiny amount by misreporting, but not much. Okay, if we can drive the degree to which you can benefit through misreporting to 0 as the number of players grows large, we're going to call this asymptotic dominant strategy truthfulness. And, if it's even a little bit easier to, just in terms of cognitive load, to tell the truth compared to try to do something strategic, you might think that asymptotic dominant strategy truthfulness is almost as good as exact dominant strategy truthfulness. And what we'll try to see is whether we can get much better revenue guarantees under this small relaxation. Okay, that's the sort of general plan for today. And the tool that we're going to use is called differential privacy. And it's this thing that you might come across in your studies elsewhere. It's usually not used as a tool for auction theory. If you have an iPhone in your pocket, it's reporting statistics back to the mothership in Cupertino, subject to differential privacy guarantees. If you participated in the 2020 census, the US government is going to release statistics from that census, which are subject to differential privacy guarantees. In general, and I'll when we go through the definition, I'll say a little bit about this. It was developed as a tool for doing data analysis with rigorous privacy guarantees, but we'll see why it's going to be useful for the problem at hand here. Okay. So by way of maybe motivation, let's try to remember what goes wrong if we try to compete with the revenue of the best fixed price in maybe the most straightforward, dumbest way possible, right? The sort of maybe first thing you would think of if I say, okay, compete with the best fixed price in hindsight on the set of bids you've received, is to just compute what is the revenue of the best fixed price on the bids you have in front of you, use the fixed price that realizes that revenue, and just charge everyone that. And if you just sort of recall, what is the revenue of the best fixed price? Well, for every price P that you might charge, the amount of money you're going to make is, well, P dollars for everyone who buys the good at that price, which is just the number of people whose value is bigger than the price. And so like plan 0, we talked about this like a while back, might just be to pick, just like solve this computational problem. It's not that hard. In fact, we sort of talked about how the best fixed price in hindsight is always exactly equal to the bid of one of the n bidders. And so if you want to compute the best fixed price in hindsight, you only have to compute this quantity for n particular values of P equal to the bids. So why don't you just compute this price and charge it? Well, the problem is that because this price is computed from the bids that were received, it is highly manipulable by at least one person, right? The best fixed price in hindsight is going to be the bid of some particular bidder, which means that by changing their bid, they could change the price that is offered to them, which means that they have incentive rather than reporting the truth to report the bid that will lead to the smallest price offered to them, which they can then take advantage of. Right? So it's not a truthful auction. And that was sort of what underlied, this sort of problem was what underlied all of the techniques we developed in the last few lectures that sort of reduced to learning, trying to sort of estimate the best fixed price from data in some sense that was independent of the bid of the agent we were offering the price to. We did that with the random sampling auction. We did that with polynomial weights. We did that with these bandit algorithms. Okay, and we sort of noticed that, at least in these simple settings, this was sort of like an if and only if condition. It's like a characterization of dominant strategy truthfulness, and because these are single parameter domains. If we want exact dominant strategy truthfulness, there's just no way around it. We've got to compute prices that are independent of bidder reports. Okay, or we can offer different prices to different people, but the price that I offer to you better not depend at all on the bid that you make if I want it to be a dominant strategy for you to report truthfully. There's just no way around that. So the tack that we're going to take in this lecture is, we're gonna go back to, this naive proposal of just computing the best fixed price in hindsight on the data at hand and charge that to everybody. But rather than like just exactly computing this, which can be highly sensitive in the bids of particular bidders, we're going to try to, like compute this quantity approximately in some robust way, basically, so that in a sense that we'll make formal the computation of the price, although it is a function of everyone's report, somehow we would like it to be, like when we compute exactly this quantity, the best fixed price in hindsight, what did we notice? We noticed that the best fixed price in hindsight was equal to the bid of some particular bidder. So in some sense, like the price we compute is independent of the bids of most of the bidders, okay? And it is like exactly equal to the bid of one of the bidders. So there's at least one person who has sort of very strong ability to manipulate the price, and a bunch of people who probably don't have much ability to manipulate the price. And so like in some sense, the thing we're going to try to do in this lecture is we're going to try to smooth out that part of the computation so that we're computing this price that maybe depends on all of the bids, but only in a mild way, so that there's no one person who has significant ability to manipulate the price. Okay, so maybe we're going to try to compute a price that is almost independent of the reported valuation for all of the players. Okay, and our hope, which we'll have to make rigorous, is that in doing this, we will get a mechanism that has very little incentive for any player to deviate. Not zero incentive, but very little incentive. And hopefully by driving that incentive to zero, we can get approximate truthfulness guarantees that become exact as the market grows large, as the number of potential buyers grows large. Okay. So next, we start getting into actual definitions. But are there sort of questions at this stage in terms of the general motivation, the kind of thing we're going to be trying to do here? Okay. So let me tell you about differential privacy, and I will introduce it in the language of auctions, but I'll try to give you a little bit of color also in how this is used elsewhere. So at a high level, what differential privacy tries to do, differential privacy, the viewpoint of differential privacy is that the input to a computation is some data set, which is like a collection of records, each of which is under the control of one person. Like you have control over whether your data is used in a computation. You don't have control over whether my data is used in the computation. And what differential privacy tries to do is it tries to compute, it tries to give you a way to compute useful things such that you can't learn in a statistical sense from the output of the computation whether the computation was run with your data input correctly, or whether it was run without your data, or maybe whether it was run with your data input incorrectly. Okay, so the like a key idea in differential privacy is the concept of sort of two what are called neighboring data sets, two neighboring data sets. On the one hand, the data set that contains everyone else's data and contains your data. Okay, that's the real data set. And then like in a counterfactual world, a data set that still contains everybody else's data, but now all of a sudden it doesn't contain your data anymore. Something else has been swapped out for your data. Okay, and the general idea in differential privacy is, you should not view it as a privacy violation if I have run a computation that didn't even have access to your data. And so if there's no way for an outside observer to tell whether I ran the computation on the version of the data set that contained your data or on this counterfactual version of the data set that didn't have your data, then you shouldn't think of that as a privacy violation either. Okay, now this notion of a neighboring data set in which everything stays the same except your data, this is why there's sort of a close connection between differential privacy and mechanism design, the way we've been talking about it. Right? This is sort of the notion of like a unilateral deviation. If you think of the data that is input to the mechanism as the vector of bids, where your bid is your data, then if you consider the world in which you tell the truth and bid your true value, and the world in which you unilaterally deviate and bid something else to try to get some gain, but everything else stays the same, then this is sort of like, well, on the one hand, the data set that contains your true data versus the neighboring data set that is identical and doesn't contain your data. Okay, so that's sort of like the connection. So let's say that two bid vectors, two data sets, but in this case, the data sets are just the collection of bids input to the mechanism by each of the parties. Right? And what are these bid vectors? That, right, a bid is a number between 0 and 1, and there's n bidders, so a bid vector is just a vector of n numbers between 0 and 1. Let's say they're neighbors. If they differ in a single person's bid, meaning there's some index I, such that these vectors v and v prime are identical in every other coordinate j not equal to I, right? Like everyone else, their bids remain the same in v and v prime, but for person I, it might be that their bid has changed between bid vector v and bid vector v prime. Okay, so like think about this as everyone else bids however they're going to bid, and in bid vector v, like person I tells the truth, they bid their true value. In bid vector v prime, they've lied, they've deviated in some way, but that's the only difference. Okay, if we've got two bid vectors like this that differ in just a unilateral deviation and just one person's bid, let's call these bid vectors neighbors. Now, what differential privacy asks for is the following. We've got a mechanism. What's the mechanism? Well, it's some like randomized algorithm that looks at the bid vectors. So the input to this thing is a bid vector. It thinks, and then it might flip some coins, and it outputs something, like it chooses a price to charge everybody, for example. And we say that this mechanism is differentially private with parameter epsilon if for every pair of bid vectors, for every set of bids for the bidders, and for any deviation that bidder I might consider making, for example, and for every outcome, for every output the mechanism might produce, like for every price it might decide to charge everybody, the probability that it produces that outcome, if the input is v, say if bidder I decides to tell the truth, should be close to the probability that the mechanism produces the same outcome if the input was v prime. That is, if everyone else maintained their bids as they were before, but bidder I decided to deviate. And close here means within a multiplicative factor of e to the epsilon. Yeah. Yeah, so at this level of generality, you could be computing anything. And people do try to compute all sorts of stuff subject to differential privacy. If you've got a data set, you could be trying to train a machine learning algorithm on it, in which case this would be the output, the parameters you've trained. You could be trying to produce tabular statistics. But in this class, what we're going to be using these mechanisms to do is to select a price to charge people in a digital goods auction. So in general, I could talk about like an algorithm that tries to do anything, and I could talk about its privacy properties. But just like jumping ahead, the way we're going to instantiate this, in this lecture is by looking at algorithms satisfying this property that are in particular trying to look at bid vectors and choose the price that maximizes revenue given the bids. Good question. Okay, so like differential privacy says the probability of observing any outcome, the probability of realizing, in this case, any fixed price, should be almost the same whether or not any single agent, whether or not any single person chooses to change their data, chooses to misreport their bid. Okay, so since this is quantified over all pairs of neighboring bid vectors, it means simultaneously, somehow the computation is almost statistically independent of the report of any single bidder, where almost means, again, there's this parameter within this multiplicative factor of e to the epsilon, which you should maybe really think of as like 1 plus epsilon. Okay, so like epsilon, we're gonna pick epsilon to be some small number. And e to the epsilon, when epsilon is small, is really, it's really sort of like 1 plus epsilon. It's sandwiched between 1 plus epsilon and 1 plus 2 epsilon. So you should think of this as sort of saying, look, like on the one hand, if epsilon was 0, right, this would be saying the outcome is, the outcome of the mechanism, the price chosen, is literally independent of everyone's bid. It cannot be affected at all by anyone's bid. Okay, on the one hand, then we'd have a truly dominant strategy truthful mechanism. On the other hand, it would be one that was completely blind. It couldn't be affected by the bids at all, so probably wouldn't do anything useful. And then this parameter epsilon in the definition of differential privacy, it sort of allows us to dial it up. Yes, it gives us something to dial up slowly to allow the mechanism to all of a sudden depend somewhat on its inputs, but to a limited extent, and hopefully lets us do useful things. Okay. So does the definition make sense? By the way, the reason this is called differential privacy and is usually thought of as a privacy definition is if you think of like an outside observer who can only observe, who can't observe the input to the mechanism, can only observe the output to the mechanism, then if the probability of the output of any particular output that I've observed is almost the same in all counterfactual worlds in which I can change one person's data to anything else, then if you think about it for a second, you maybe write down Bayes' rule, you realize I really can't infer very much about any single person's data. Okay, so that's why this is normally thought of in the context of privacy. Okay, but for us, we're not interested in privacy. We're interested in using this to design approximately truthful mechanisms. And so I want to think about what we mean by approximate dominant strategy truthfulness and what the connection between approximate dominant strategy truthfulness and this notion of differential privacy is going to be. So I'm going to write down sort of a strong definition of approximate dominant strategy truthfulness that should hold basically simultaneously for all possible utility functions. So suppose we've got a mechanism of the form that we have on the previous slide. So it takes as input a collection of bids, say, and it does something. It chooses some outcome in some arbitrary outcome space O. Just to keep a concrete example in your mind, the one we're going to use is it chooses a price, and then that price is going to be the price that an item is sold for. Okay. Now, people might have, in general, preferences over the outcome, right? Like people might have preferences that depend on their own value and the outcome that is chosen, right? So for example, I have like a utility function that depends on how much I value the item being sold. That's my own private secret. And also depends on the price that the item ends up being sold for, because that determines whether I can buy it and what my utility is if I have the opportunity to buy it. So in general, we'll sort of think of utility functions as being mappings from, on the one hand, like a private type, like how much you value the item, a number between 0 and 1 in this case, and the outcome chosen, like the price I end up selling the item for. And they map these two objects onto a number between 0 and 1, how happy you are with this outcome. And we'll say that this mechanism for choosing an outcome, for choosing, for example, a price, is epsilon approximately dominant strategy truthful if simultaneously for every bidder I, and simultaneously for every possible utility function that they might have, and for every vector of valuations, for every vector of bids that might be output to this mechanism, that might be input to this mechanism, and for every alternative report that bidder I might consider making, for every deviation from truthful reporting that bidder I might consider, if we think of V as the vector of valuations that results when everyone else bids as they were going to and bidder I tells the truth, and V prime as the vector of valuations that results when, again, everyone else bids however they were bidding, but bidder I unilaterally deviates to bidding something else, to bidding V prime I, then it should be that bidder I's expected utility for telling the truth, it's an expectation because the outcome is chosen from what might be a randomized mechanism, is at least bidder I's expected utility from deviating. Right? The difference between the left-hand side and the right-hand side is the outcome is now chosen from the mechanism that had bidder I's misreport entered into it, minus epsilon. Okay, so they might have been able to gain a little bit by deviating from the truth, but not by more than epsilon. So it's telling the truth is always an epsilon best response. And since the mechanism doesn't know players' utility functions up front, I mean, that's the whole point. It's trying to get people to bid truthfully, but they might not. We're asking for this guarantee to hold not just for the particular utility functions that happen to be realized by the bidders, but simultaneously for any possible utility function they might have. Okay, so does that make sense? We're asking that truth-telling not always be an exact best response, but always be an epsilon best response over the randomness of the mechanism, no matter what your utility function should be. For all utility functions, and for all bids of your opponents, truth-telling should be an epsilon best response and expectation. Yeah. Yeah, I guess you could encode the value as, hard-coded into the utility function. Sometimes convenient not to, but it's the same thing. Other questions? Okay. So people can, potentially, benefit by misreporting, but not by much, not by more than epsilon. Okay. So the reason that differential privacy is going to be useful for us in this lecture is because differentially private mechanisms will automatically be epsilon approximately dominant strategy truthful, okay, in generality. So sort of a theme in this course has been reduction from the problem of mechanism design to the problem of algorithm design. Right. So for example, when we characterized single parameter domains, and we said, well, a mechanism in a single parameter domain is truthful or can be made truthful with payments if and only if it's monotone, then we sort of, what we did is we saved ourselves from having to think explicitly about truthfulness as a constraint And we put ourselves in the position where we could just try to design monotone algorithms. That was how we got truthful mechanisms for the knapsack problem, for example. This is going to be something similar. Okay, if differentially private mechanisms are automatically approximately dominant strategy truthful, then we can sort of, again, stop thinking about truthfulness separately as a design constraint, and then just focus on the algorithm design problem. How do I design a differentially private algorithm for solving some problem, like approximating the revenue of the best fixed price? Okay, that's the sort of high-level outline of the strategy here. Like a generic reduction from a mechanism design problem to an algorithm design problem. So here's the theorem we're gonna note. It's gonna be relatively immediate. And it's that if I've got a mechanism really of any sort that maps bids to like arbitrary outcome spaces, and the mechanism happens to be epsilon differentially private, then it's also epsilon approximately dominant strategy truthful. Okay. So how come? Let's go through it. So remember what we need to show, right? Like there's all these buyers and they might have utility functions we don't know about, but the utility functions map, their own value and the outcome to some number between 0 and 1. And the effect that they, so their utility function depends on two things: their value, which they have no effect, no ability to change, like they were born with it, and the outcome of the mechanism. The outcome of the mechanism is the thing they can potentially try to change, right? Their report feeds into the mechanism, which chooses the outcome. And so what we need to show is that they can't substantially increase their utility by misreporting through this channel of influence they might potentially have, in which their misreport is fed into the mechanism, which then chooses a different outcome or a very different distribution on outcomes. Okay, so let's focus on a particular buyer I and a particular vector of bids V. And let's just, and a particular differentially private mechanism M, and let's just directly compare, like, buyer I's expected value if he tells the truth with his expected utility if he deviates. So let's start with his expected utility if he tells the truth. Okay, it's his utility in which we plug in, on the one hand, his true value. That's not something he can change. I mean, he can lie about it to other people, but he can't lie about it to himself. Like his true value is always the one that's plugged into his utility function when we try to figure out how happy he is. And then the other input to his utility function is the outcome. That's the thing he can try to change. And it's drawn from this distribution, the distribution on outputs by the mechanism that is induced by the bids of everyone, including him. And so just expanding out the expectation, well, all this is the sum over all of the possible outcomes that might result. For example, the sum over all of the prices that we might decide to charge for the digital good that we're selling, of the utility that he would experience if that outcome was chosen, times the probability that outcome was chosen. That's just what an expectation is. Now we know from differential privacy, like what does differential privacy say? Well, it says that if player I unilaterally deviates and changes his bid to something else, okay, he misreports, then the mechanism was not very sensitive to his bid in the sense that the probability of any particular outcome, the probability of choosing any particular price for the good, for example, would change by at most an e to the epsilon multiplicative factor because of his misreport. So if he misreports, okay, right? So the input to the mechanism is v prime rather than v. Well, the probability that this mechanism under his misreport produces some particular outcome O, chooses some particular price to charge, is the same as it was before, except possibly larger or smaller by an e to the epsilon factor. Okay, so in the worst case, if we're thinking about how much his utility can decrease, for example, it's larger than the probability it was before times e to the minus epsilon, right? That's like making the probability smaller by an e to the epsilon factor. Okay, so pulling out this factor of e to the minus epsilon, this is just, since this happened event by event, the probability event by event changed by at most this e to the epsilon factor. This term is just e to the minus epsilon times player i's expected utility if he deviates, he misreports. Okay, because that causes the outcome to be drawn from the distribution induced by the mechanism when its input is v prime. And, got all that? Because e to the minus epsilon is at least 1 minus epsilon, and because the utility functions are bounded between 0 and 1, we can turn a multiplicative change of e to the minus epsilon into an additive change of epsilon, right? I mean, this is at least a multiplicative factor of 1 minus epsilon, and since the utility function is a number that is at most 1, losing a 1 minus epsilon factor is only less than losing an epsilon additive term. Okay, so basically immediately we see that if the mechanism was epsilon differentially private, it basically says player i's utility player i's report probabilistically has very little effect on the probability of any outcome chosen, and so his utility, he cannot affect his expected utility, which is just this linear function of the probabilities of the outcomes chosen by very much by misreporting. Yeah. Oh, because we're going to be designing mechanisms that are randomized. Like in order for, like one implication of sort of the definition of differential privacy is that if the mechanism is going to do anything interesting, like it's not just going to be like a constant function, it's going to have to be randomized, right? Because otherwise, because suppose the mechanism wasn't randomized, then, and suppose it also wasn't a constant function. So like it was possible to cause it to do at least 2 different things. That would mean, on some input, it deterministically does thing 1. On some input, it deterministically does thing 2. And if you consider like walking between the input that causes it to do thing 1 and the input that causes it to do thing 2 by changing each person's part of the input 1 at a time, you'll eventually get to 2 neighboring inputs that differ in just 1 report. So that, like, say you are pivotal. If you report the truth, then the mechanism does thing 1 deterministically. And if you misreport, the mechanism does thing 2 deterministically. And that would be a violation of differential privacy. Because for thing 1, the probability of it occurring would be 0 on one side of this equation and would be 1 on the other side of this equation. And, even for very large epsilon, 0 times e to the epsilon is 0. And that's exactly the kind of thing we're trying to avoid when we care about incentives, right? We're trying to come up with a situation where we're going to pick a price to charge everybody. And we don't want anyone to be pivotal, right? So like, it's a bad situation for incentives if you can unilaterally change your bid and deterministically change what the price is, because then you're going to want to do that to cause the price to be lower. And so if we want that to never be possible, right? If we want it to never be possible that someone can deterministically or with significant probability change what the price is by misreporting, and we want the mechanism to do something interesting, like, you know, there should be at least 2 possible prices that it might output, then it's got to be randomized. There's no way you can have a deterministic mechanism that has those properties. Does that make sense? Good question. Yeah, so these are necessarily going to be randomized mechanisms. The randomness is very important. That is the means by which we are going to be able to sort of enforce that no matter what the bids are, no person's bid is substantially pivotal. No person's bid has substantial probabilistic effect on what the outcome is. Does that make sense? Okay. So, you know, our goal is to design an approximately dominant strategy truthful mechanism that has high revenue. But now that we know this fact connecting differential privacy and approximate truthfulness, we've sort of reduced to hopefully the easy problem of designing a differentially private mechanism that has high revenue. And so, okay, you know, differential privacy, we need randomized mechanisms. So let's like think for like half a second about what such a mechanism like might look like. So again, maybe the first thing you would think of is you'd sort of think, okay, well, why don't I compute like on the data, like what is the price that maximizes revenue? It's a deterministic computation, so you know that can't be differentially private. But then maybe I'll just like add noise to that price. Maybe I'll add like a little bit of noise to that price, and maybe that'll be like differentially private. And maybe also it'll still have high revenue. And there's a couple of problems with that proposal. But one of them is, yeah, so the 2 problems with the proposal is it won't be differentially private and it won't have high revenue. But like let's just sort of think about what we know already. Like we sort of know that adding noise to the price in some naive way, like can't possibly be a good idea. Because we've seen examples where changing the best fixed price by even a little bit can cause drastic decreases in the revenue obtainable. Right? Like suppose I have learned that 99% of the people in this room view dongles of this sort as, you know, worth $5. Then it might be that the best fixed price to sell dongles of this sort is to charge $5, and you know almost everybody buys them. But if I were to perturb that price a little bit and charge $5.01, then all of a sudden my revenue might sort of drastically decrease because all of a sudden like almost nobody would be willing to buy them. Okay, so separately from the fact that like adding noise to the price wouldn't produce a differentially private mechanism, like it would also like ruin the revenue of the price. We wouldn't have adding noise in this way might give me like a number that is close to the value of the best fixed price, but the number that I got would not itself be an approximately revenue maximizing price. Okay, so like when I'm trying to approximate the revenue maximizing price, it's not just that I want to be close numerically to a revenue maximizing price. I actually want a price that will make me approximately optimal revenue. And so the thing that I really want to do is a little bit different. Rather than computing like the revenue maximizing price and add noise to that, like what I sort of implicitly want to do is for each price, compute the revenue I would have made had I charged that price. And I want to like select amongst these prices sort of randomly somehow, where I'm more likely to select prices that make me more money, and I'm less likely to select prices that make me less money. And I'd like to weight the scales so that I select prices that make me more money, sort of with weight that is as high as possible, subject to this constraint that I still have to be differentially private. Like in the limit, I want to, in the limit, I'd want to put like, with probability 1, I'd like to pick the price that exactly maximizes revenue and, never do anything else. That wouldn't be differentially private. On the other end of the spectrum, I could just pick a price uniformly at random, ignoring the bids. That would be perfectly private, but, not very good for revenue. And what I want to do is something sort of in between, where I'm not picking like a uniformly random price, but I'm sort of, tipping the scales towards the revenue maximizing prices as aggressively as I can within the bounds of needing to be differentially private. Okay. So like, in the last few lectures, we've run into this problem a few times where there's like continuously many prices between 0 and 1. In this lecture, actually, we could directly work with all continuously many prices, but just to make things a little simpler, let's pick some finite subset of prices to work with, and then at the end, we'll pick what that finite subset is in the same way we've done for the last few lectures to manage trade-offs. So here's the idea. And it's going to be an instantiation in this sort of auction problem of a more general technique from differential privacy called the exponential mechanism, which you can generally use to pick good outcomes of any sort in a differentially private way. Here we're going to instantiate it so that the objects we're picking are prices, and goodness is measured as a function of revenue. But like in general, you could go through this exercise in all sorts of different settings, like picking machine learning models that have low classification error. Okay. So the idea is the following. So it's going to be a randomized mechanism. It's going to take as input a vector of bids v. Okay. It's going to choose a price from this finite set of prices. And it has this parameter epsilon, which is going to control the level of privacy it promises and thereby the level of approximate truthfulness that it guarantees. And what it's going to be trying to do is it's going to be trying to pick a price that maximizes some particular objective. In this case, the objective is revenue. So, like given the bids and given a price P, the revenue that we obtain from price P is just a number that we can compute from the bids. It is P, the amount of money we would make per sale, times the number of people whose values exceed P, the number of people who would be willing to purchase at that price. Yes. Capital P is the set of prices that we are going to be selecting from. That we'll have to figure out, at the end of this, there's going to be some trade-off of the sort that we've had in previous lectures where, we're going to have a theorem that says, look, we get revenue that is competitive with the best price in this set P up to some like loss that depends somehow on the size of P, and we'll have to deal with that at the end. Okay, but like for some price P and for some vector of bids V, we can just like figure out how much money we would make at that price given these bids. And one thing I want to note, something that's going to become relevant in the analysis, since we have to think about the effect of unilateral deviations on this algorithm. Like, how's the algorithm going to behave differently if someone changes their bid? It can be that the identity of the best fixed price, the revenue maximizing fixed price, swings wildly if one person changes their bid, right? Like we've seen examples in class where things are exactly, where there's an exact tie for two prices that could be the best fixed price, either selling to everyone at $1 or selling to the top 10 bidders at $10. We've seen examples like that. So one person's bid can have a big effect on what the best fixed price is, like as a dollar amount. But if at a particular price P, if you look at how much revenue I would make if I sell at this particular price P, one person cannot have a very large effect on this. Because, well, P is a number between 0 and 1. And we're multiplying it by the number of bidders whose value is above P. And by misreporting your bid, you can change this number of bidders whose value is above P by at most 1, because you could cause yourself to be one of those bidders or not, but you have no effect on whether the other bidders are above this price or not. So the nice thing about this revenue objective is that, at least for every particular price P, no single bidder can have a big effect on the revenue that we would make if we charged price P. So the thing we want to do is we want to randomly output a price that upweights prices that lead to high revenue and downweights prices that lead to low revenue, and does so as aggressively as possible, subject to this constraint that a single person changing their bid, which can change the revenue of any particular price by at most 1, doesn't change the probability of outputting that price by more than e to the epsilon. And so what we do is we define basically that distribution. All the algorithm does is it randomly outputs some price P, where the weight that we assign to price P is proportional to e to the epsilon. Okay, epsilon's our privacy parameter, times the revenue we make if we charge price P. Okay, and then we just normalize the thing so that this is a probability distribution. Okay, so we're just outputting a price randomly, where we are sort of putting more weight on prices exponentially fast in proportion to their revenue, in proportion to epsilon times their revenue. Okay, so if epsilon is 0, then all prices are the same. We just output the uniform distribution on prices. But as we start making epsilon very slowly bigger, all of a sudden we are outputting under this distribution high revenue prices much more likely than low revenue prices, because exponentials grow very quickly. Okay, so the mechanism is very simple. I look at the bids. I compute the revenue under these bids for each of the fixed prices I might charge. And then I just randomly pick a price according to a distribution that puts weight on each price sort of in proportion, exponentially in proportion to epsilon times the revenue obtainable at that price. And that's it. Does that make sense? Okay. And so the claim is that the mechanism is differentially private. And in particular, it gives us a way of choosing a price as a function of the bids that makes truth-telling an epsilon approximate dominant strategy, because of this connection we've proven between differential privacy and approximate dominant strategy truthfulness. Okay. So let me just, we're gonna derive this in a second. Let me just like stare at the form of this distribution for a second, just to foreshadow the, a couple of lines of algebra. So what is the probability we output some price p? Well, I said, well, it's, it's proportional to e to the epsilon times the revenue obtainable by that price p. But a probability distribution has to sum to 1, right? Like the sum of outputting, all of the possible prices, it's got to be 1. And so to make that a probability distribution, I have to like divide this by something, which is just, the weight, like there's the weight I'm assigning to price p. And then I have to divide that by the sum of the weights I'm assigning to all of the prices. Okay, just to make this a probability distribution. So I just want you to note that like the probability we output some price p, the thing that it looks like is, there's a term that's like in the numerator, e to the epsilon times the revenue of that price. And then in the denominator, there's the sum over all of the other prices of a term that looks just the same, e to the epsilon times the revenue of that other price. Okay. So let's prove that this exponential mechanism is differentially private. And remember, what is the thing we need to prove? We need to show that for any price p, for any bid vector v, and for every neighboring bid vector v prime that results from any single bidder unilaterally deviating and misreporting some other bid, the probability of outputting price p remains almost unchanged, changes by at most an e to the epsilon factor. Okay. So let's just compute. What is the probability that we output this price p? Well, that we can just look up from the definition of the mechanism. The mechanism, the way I defined it, it literally just assigned the probability that we output price p. It was this thing that was, proportional to e to the epsilon times the revenue produced by price p. Now remember what we noticed about the revenue of a fixed price. If one person deviated, if one person changed their bid, that would change our estimate for how much money we would make charging a fixed price p by at most 1. Because it would change the number of people willing to, like if the price is 75 cents and you change your bid, you've changed the number of people willing to buy the good at 75 cents by at most 1. Like at most, maybe you're no longer willing to buy it, but you haven't changed everyone else's willingness. And the price was a number between 0 and 1. So if the price is between 0 and 1, and at most one person has changed their willingness to buy the good, then the revenue changes by at most 1. And so I know that the revenue that I make at price p is at most, when the bids are v, and before you've unilaterally deviated. Well, it's at most the revenue I would make after your unilateral deviation, plus 1. Maybe after you deviate, the revenue goes up or down by 1. Okay. And so this plus 1, it's like appeared inside an exponent. So if I have like e to the a plus b, that's the same thing as e to the a times e to the b. So, I've got e to the epsilon times the revenue I would make if you deviated over 2, plus e to the epsilon over 2 times 1. So I can pull this e to the epsilon over 2 outside as a multiplicative factor. Now we've got this normalizing term. Oh, yes. Yeah, so we could be a little bit tighter, like, it's really plus p, but p is at most 1 because we've scaled all of the utilities to be between 0 and 1. But you're right, like for small prices, this is being loose. Okay. Now, like we've got this normalizing term too. But remember, what does the normalization, what does the denominator look like in the expression for our probabilities? Well, it looks just like the numerator, except it's summed over all of the other prices. And so we can perform exactly the same maneuver in the denominator. One person's unilateral deviation has changed the revenue that we could make at any fixed price by at most one, which allows us from each term in the denominator to pull out this very same e to the epsilon over 2 factor. So we can pull out another e to the epsilon over 2 factor from the denominator as well, and get the denominator that would have resulted had bidder I unilaterally deviated. And so combining these two terms hello? We get that the probability that we choose some particular price P when everyone tells the truth is at most an e to the epsilon factor away from the probability that we choose the same price P when any one person chooses to lie, chooses to deviate. And that is the definition of differential privacy, that the probability of any outcome, in this case a price, cannot substantially change as a function of the report of any single bidder. So we've proven that this exponential mechanism, this sort of simple method of randomly choosing prices as a function of the bids to try to maximize revenue without being too sensitive to the bids of any particular person, has succeeded in being differentially private. And therefore, we have an approximately dominant strategy truthful mechanism. Okay. Okay, so it's like an approximately dominant strategy truthful mechanism, but that's not too impressive just yet. Like if I just wanted a dominant strategy truthful mechanism, I could just throw away the bids and pick a price at random. And so this is only interesting if we can simultaneously with approximate dominant strategy truthfulness, come close to maximizing revenue, come close to like competing with this revenue maximization objective. And so we can, and so that's the second theorem I want to prove, which is that for any set of prices that we want to compete with, P, and for any set of bids that we actually receive, which hopefully are close to the true bids now that we've established that the mechanism is approximately dominant strategy truthful, and for any parameter epsilon, this is the knob we get to turn to sort of trade off the revenue of our mechanism with its truthfulness guarantees, that with high probability, with probability 1 minus delta, this mechanism doesn't just choose any price, it chooses a price that actually obtains revenue that is at least the revenue of the best price, minus this term that minus this sort of term that scales logarithmically with the number of prices we were selecting amongst, and linearly with 1 over epsilon, the privacy parameter, this knob that we get to turn. Okay, so it's going to pick a pretty good price too. And the hope, and just sort of, comparing this with what we already know how to do with exact truthfulness, what we already know how to do has some, loss term that sort of scales with like square root the number of bidders. And so the hope is that we'll be able to set these remaining parameters to do better than that, while still being able to take this epsilon parameter to be something tending to 0. Because remember, epsilon controls how much people can gain by deviating. So ideally, we can take epsilon to be something approaching 0 as the number of bidders gets large, so that people have like essentially no incentive to deviate, and still get better revenue guarantees than we knew how to do before. Okay, so let's prove this. So there's some price in our comparator set that maximizes revenue. Let's call that price P star. Now, we're not going to get revenue that's exactly competitive with the revenue we would have gotten from P star, but we don't want to do too much worse. Let's call X sort of the threshold that we don't want to do worse than. So the thing that we're interested in showing is that the probability that we get a price back whose revenue is less than X is small. Okay, we want to set some like worst case revenue bound and say with high probability we don't get revenue worse than that. So I'll start with sort of a stupid maneuver. I'm interested in bounding the probability that the revenue for the price I choose is less than X. And I'll just say, well, probabilities are all less than 1. So if I divide this thing by like another probability, I'll only get a bigger number. Okay, so I'll start off with a dumb move. I'll say, okay, well, the probability that I get revenue less than X, it's at most the probability that I get revenue less than X divided by the probability that I get the exactly optimal revenue. Because, dividing by something at most 1, less than 1, it's only making the number bigger. Now, if I want to upper bound this, I want to upper bound the numerator and lower bound the denominator. So what's the probability, what's the worst case probability that I make at most X dollars? Well, in the worst case, every single price makes me at most X dollars. And right, so I'll sort of, adding up the probabilities of all of these bad events, I'll have to add them up over all of the prices. In the worst case, every price earns me at most X dollars. And remember, the probability that I output a price is increasing in the revenue it earns me. So really, the worst case for this numerator is that every single price makes me exactly X dollars. Because then this event in the numerator that I get a price that makes me at most X dollars has contributions from every single price, and those contributions are maximized. The probability I output something is larger the higher its revenue, and a price is contained in this event in the numerator only if the revenue is at most X. So the worst case is the revenue is exactly X. Okay, so in the numerator, this probability is proportional to, at most, well, for every single one of the prices I'm considering, the probability proportional to which I output that price, which is at most e to the epsilon times X over 2. And in the denominator, well, the worst case, it might be that there's more than one price that gets me the optimal revenue. But in the worst case, there's exactly one. And the probability that I output that single exactly optimal price is just proportional to e to the epsilon times the revenue of that price over 2. And the reason, by the way, that we're looking at this ratio, that we sort of perform this dumb maneuver of dividing by this other probability, is because remember all of these probabilities that we were sort of carrying around had these like normalization terms that caused them to actually sum to 1. Those terms are sort of annoying. And so by looking at this ratio, those cancel out and we don't have to worry about them anymore. But now we're sort of in business. Exponentials behave nicely. E to the a over e to the b is just e to the a minus b. And so, this ratio of exponentials, I can just write as e to the epsilon times x minus the revenue of the optimal price over 2. And all of this is multiplied by the number of prices I'm choosing amongst. And if I just choose the value of x for which I want to prove the theorem, I want to prove that with high probability, I get revenue that is at least the optimal revenue minus 2 over epsilon times log of p over delta, and plug that in here. Well, what happens? The optimal revenue cancels out. And what I'm left with is just that the probability that I get a price whose revenue is at most x is at most the number of prices I'm selecting amongst times, well, e to the minus log of p over delta. And exponentials and logs are inverses of one another. And so this exponential is going to cancel out with this log. And I'm just going to get the number of prices times delta over the number of prices, which is just delta. Okay, so the probability that we get a price that gives us revenue that is worse than the optimal price minus 2 over epsilon times the log of the number of prices I'm choosing amongst is small, it's at most delta. Okay. So just putting it all together, we now have a simple randomized method for looking at bids, selecting randomly a price that approximately maximizes revenue, at least in comparison to this, at least with respect to this finite comparison class P, and is approximately truthful. But we've got to go through this same exercise we have in the last 2 lectures of deciding what set of prices P to compete with. Because the more prices we compete with, the closer the revenue of the best fixed price in this set is with the revenue of the best fixed price overall, but we pay for it in our bounds. We know how to do this. But our dependence on the number of prices is now only logarithmic, which lets us get a somewhat better bound than we've gotten before. So in particular, if we consider the same set of discretized prices we've considered over the last few lectures, right? Like not all of the continuously many prices between 0 and 1, but alpha, 2 alpha, 3 alpha, up to 1, right? There's 1 over alpha many such prices. Like we know, just as we've used this fact a few times already, that the revenue of the best fixed price within this benchmark set is at most alpha n worse than the revenue of the best fixed price overall. And so plugging that in to our bound and optimizing over alpha, we can get that with high probability, like 99% of the time, we've got a mechanism that's able to select a price that gets revenue that is worse than the revenue of the optimal price by at most log n over epsilon, where n is the number of bidders. And there's one more parameter here, epsilon, right? Like that's a parameter, we get to choose it. And it's not like we can just choose it optimally the same way we chose the parameter alpha, right? Like epsilon is mediating the trade-off between 2 different things. Right? It's mediating the trade-off between revenue. The smaller we make epsilon, the worse our revenue gets, and incentives. The smaller we make epsilon, the better our incentive guarantees are, because people have an epsilon incentive potentially to deviate. Right? So there's this remaining knob we can turn. We can make deviations less profitable for individuals, but by doing so, we weaken our incentive guarantees. But there are still sort of attractive ways to set that knob. So for example, right, like we can take epsilon to be something that goes to 0 as a function of the number of bidders. Right, like we can take epsilon to be, for example, 1 over log of the number of bidders. In which case, the revenue that we get is still much better than the revenue we were getting before. Remember, for an exactly dominant strategy truthful mechanism, what we showed how to do was to get revenue opt minus square root of n. Right, so if we set epsilon to be 1 over log n, we get opt minus log squared of n, which is exponentially better. But still, as the market grows large, as the number of potential buyers in this auction grows large, the incentive to deviate tends to 0. So we can still get an asymptotically truthful mechanism, by which I mean the incentive to deviate from truth-telling tends to 0, as the number of potential buyers gets large, as you consider selling Microsoft Windows to 100 people, then 1,000 people, then 1 million people, then 1 billion people, right? N could be quite large. The incentive to deviate becomes negligible. And in exchange for that, in exchange for allowing a small but negligible incentive to deviate, what you get is, sort of like an exponential improvement in your loss compared to the optimal revenue. You went from root n to log n. Okay. That's it. And I'll see you guys next class.